Okay, this is the first video of AP Physics 1. And as you go through this, make sure you're taking notes as you listen, because this is what we're going to talk about in class, is just the information that's presented on here. Also, below this video is going to be a set of questions as like a formative assessment. You need to score 80% on all of these assessments to really be ready to take your Unit 1 exam. So again, you can pause this and answer the questions as you go. Also at the end is a spot to ask questions, and if so, you can think of them like questions you'd have during a lecture. So as you're listening to this, if you want to just pause it, and at the very bottom of the formative assessment, type in the question, and they will be answered in class. Okay, here we go. So the first section is really kind of just a look at what motion is. And again, it says here, motion is the change of an object's position or orientation with time. And the path that it follows is a trajectory. Okay, so whether it's a straight line, circular motion, this arch called a projectile motion, or something that spins, rotational motion. And we're going to talk about all of these during this course. They all follow what's called a trajectory. So these all have different trajectories. All right, so we've got three different diagram pieces here that shows three different types of motion. The guy on the skateboard, if you notice, the gap between each picture is pretty uniform. So that indicates that the object is moving at a constant speed. If you are familiar with the word speed, speed is how much distance you cover in a given time, how far you go in a certain amount of time. So if you go 100 meters in 10 seconds, your speed would be 100 meters divided by 10 seconds, or 10 meters per second. Okay, so this first guy is moving at as a constant speed. He gains the same amount of distance in every time interval. So each picture here is a given time interval. The middle one, the runner girl here, as you can see, from the first to the second, second to the third, third to the fourth, she's getting farther apart for each picture. So that means she's speeding up. She's covering more distance in the same amount of time. Okay, and for the car here, the reverse is true. For each picture, they're covering a shorter amount of distance, so they're slowing down. Okay, so again, for each of these pictures, each picture represents a given time interval, and it's the same time interval between pictures. But if the distances between are constant, it's going at a constant speed. If the distance intervals are increasing, they're speeding up. If the distance intervals are decreasing, they're slowing down. Okay, now this we have to look at. If you shoot a basketball, you'd have to look at it moving in two dimensions, not only to the right, but up and down as well. So you'd have to look at two different directions of motion here. Okay, and if you look to the right here, if we can kind of imagine the distance between each ball going to the right, they're almost the same. So going to the right, the motion is pretty equal. However, if you look at vertical distance differences, as it goes up, the distance going up decreases as the ball goes up, which means that it's slowing down in an upward direction. And as it comes back down, it's speeding up because the pictures are getting farther apart. We'll be talking about this in more detail later on. Okay, so we can look at, instead of looking at cars and bowling balls and runners and things like that, we can look at it as what's called a particle model of motion, just putting a dot. Okay, so if you start off with this motion diagram of this car here, you can put it as a dot, where a dot simply represents the object, and each dot represents the same amount of time. So if this is 0 seconds, maybe this is 1 second, 2 seconds, 3 seconds. Whatever time interval you're using, you just have to be consistent. Okay, so for this, like the car up above here, the gaps are decreasing, which means that it's slowing down. Okay, this is the basketball. Okay, and these arrows are called vectors. Okay, a vector has a direction, and this v is a magnitude, so it's a number. Okay, I know there's a lot of information on here, but there's two things I want to break down on here. If you look at the vertical component, the Vy portions, if you notice, this one starts really big, and then the Ys start decreasing. So that indicates that we're slowing down vertically. Okay, if we look at the horizontal portion of this, the horizontal arrows are pretty consistent all the way across, which indicates that the object is going at a constant speed horizontally. Okay, so again, if these arrows decrease, it's slowing down. Really, and then if you notice over here, as it comes back down, the arrows get bigger, so it's increasing in speed going down. Okay. So the next step from the dots is to draw these arrows. Okay, the next section is kind of more of the motion diagrams. Okay, so if we look at a position, something called position and distance. Okay, so we have a 0 point that we made this building. Okay, so that means there's a going to the right and going to the left. Okay, this is all subjective and all relative. Okay, so the position, as we're talking about here, this car is plus 4 miles from this 0 point. The cow is -5 miles from the 0 point, which means that the cow is 9 miles from the car. Okay, you need to have a 0 point, just like on a number line, you have to have a 0 point. And if you can go either side of it, one side has to be positive and one side has to be negative. Now, some of you are thinking, can we just put the building over to the left side and make this 0? Yes. Okay. The 0 point is kind of is a relative position. Okay. All right. So then we have this running lady here. Okay. So races are easy. Typically, the start is one spot, and if you're not going around in a circle, your finish is in a different location. Sorry about that. Okay, so we have this coordinate system here, and we have our distance, and then if we can have different locations of her, that would give us our times, and we could figure out her motion, her speed and velocity. Okay, so again, here's the particle model of for the motion diagram. Every dot represents the same amount of time. So in this case, because the gaps are getting smaller over here, the object is slowing down. From 0 to 1, 1 to 2, these are staying the same because these gaps are equal. Okay. You're going to get some practice on this with your formative assessment. Okay, so again, just showing another one. Okay. So change in position from a given spot is called your displacement. Okay. And again, the displacement is simply the difference between the final position and your initial position. So in this case, if we're going this way, if we're going to the left here, we have a displacement. Okay. Now, if you think of it this way, if you go around a track, the displacement is the difference between final position and initial position. If you run 100 meters around a track and start right where you finished, your displacement was 0 because it's your change of position. So distance is just how far you go. It doesn't matter if you go left, right, back, forth. Okay. Displacement is how far you are from where you started. Okay. We have to look at the time intervals. And we have to look at this, the time intervals are always positive because we can't really make negative time. All right, so we're going to do this little sample problem here. So we have this bicycle ride. And Carol is going on a ride. Carol's 3 miles east of the water tower. A half an hour later, she is 2 miles west of the water tower. So here's our diagram. And we want to figure out her net displacement during that half hour. All right, so but we want to make drawings like this because they're actually going to show up on your AP exam. Okay. So she starts off 3 meters or 3 miles east of the water tower. The water tower is your 0 point then. And after half an hour later, she's 2 miles west. Okay, so here's your diagram. So hopefully you're seeing that her net displacement is a negative 5 miles. Okay, from where she started, negative going to the left. Okay. And then if we look here, we can see that from our drawing up above, that she moved 5 miles from her starting position. So she travels 5 miles and a half an hour. Okay, and if you think about that, that's 10 miles an hour, which isn't terribly unreasonable for a bicyclist. Okay, so again, displacement is how far you are from where you started. Distance is just how far you travel. Okay, and velocity is your displacement divided by your time. So how far do you go divided by how much time it takes to get there. That's your velocity. Okay, we're going to do a little bit of just significant figure, scientific notation, and unit piece, and then we'll move on. Okay, so precision is how consistent your answers are to each other. Okay, and this measurement tool called a caliper is precise to 0.01 millimeters. Okay, hopefully you've talked about precision versus accuracy before. Precision is how accurate your answers are to each other. Accuracy is how close your answers are to the accepted or the given value. Significant figures, hopefully you've covered significant figures in chemistry and you remember that. If not, we're going to do a little bit of review on that here. Okay, so significant figures. Anything that's non-zero is a significant figure. Okay, when you multiply significant figures together, your answer is going to have the least, your final answer can only have the same number of significant figures as your least significant figure answer. So like this one has 3 significant figures, 5.7 only has 2 significant figures, therefore my answer can only have 2 sig figs. When you add and subtract, you actually take the one that has the lowest amount of significant figures to the right of the decimal point. Okay, so 18.54, it says here has 2 decimal places past to the right of the decimal point. 106.6 only has 1, so your final answer can only have 1 place past the decimal point. To the left, it doesn't matter how many you get. Okay, when you add and subtract, it's just how many you go to the least number of places to the right of the decimal. The left, you can be as big as you need. So this also goes for subtraction as well. The multiplication rule goes for multiplication and division. All right, so scientific notation, I think you've written these before, like 3 times 10 to the 8th, 6.02 times 10 to the 23rd, those kind of things for scientific notation. Okay, so hopefully you've done things like this, where you can convert from a large number to scientific notation. Okay, so if we have 6,370,000, we want to make the number between 1 and 10. So we slide decimal point to the left, 1, 2, 3, 4, 5, 6 spots. So our first number here is where we place our decimal point, so 6.37 times 10 to the 6 meters. Okay, 10 to the 6 means it's a big number. -6 is a small number. Okay, hopefully you have had experience with this, and we will go through practice on your calculator on how to put them into your calculator correctly. All right, so again, just a little abbreviate unit review here. The unit for time is seconds, unit for length is meters, unit for mass is kilograms. Notice it's not grams for mass because a gram is small. Okay, so this is what we're going to deal with a lot for the units in this particular class, like you've seen in other science classes as well. Okay, so when you do a unit conversion, so if we want to do miles to kilometers, you'll be given this conversion factor, and then it's just unit exchange. So we have a mile in the numerator. We need a mile in the denominator to cancel out. So we have 1.609 kilometers is 1 mile. We know that works because our miles cancel out, and we're left with a kilometer. But because really this should be 60 point with a decimal point here to represent 2 significant figures. Okay, again, if you need practice on it, you can look on page 15 of your textbook for practice. All right, so then there is some estimation that we're going to do here. It'd be a good idea to have this kind of in your head when we talk about approximate relationships. So like a kilogram is about 2 pounds. There's about 3 feet in a meter. Okay, 5 kilometers is about 3 miles, 3.1 miles. A meter per second is about 2 miles per hour. So when you're thinking about if something sounds right for an answer in metric, you can kind of come back to this approximation and go, all right, does that sound right? So like, let's say you have a snail, you figure out the speed of a snail at 10 meters per second. Well, that's a 20 mile an hour speed for a snail. Probably not accurate. Okay. Now, kind of look at how fast you walk. Okay, estimate how fast you walk in meters per second. So, kind of, we need to figure out a distance and a time. So let's say you travel a mile in about a half an hour. Okay, so if you look at this, that's mile divided by half to 2 miles an hour. But we want that in meters per second. So you need to convert miles per hour to meters per second using conversion factors, which you should hopefully know. And it shows you that you move about a meter per second. Okay, if you think about this, your stride length is about a yard, about a meter. Okay, some of you will be shorter, some of you will be longer. Okay, the last section for this chapter 1 is on velocity. We talked about a little bit in the early part. Okay, velocity is displacement over time. Now we're going to look at that in little bit more detail here. Okay, so motion at constant speed is called uniform motion. Straight line motion, uniform motion. Okay, and speed is just straight line distance divided by time. There you go. That's your speed. Okay, so we have a sample problem. Jane walks at a rate moving 3 meters in 3 seconds at t0. She passes x equals 1 mark. Draw her motion diagram from t equals -1 to t equals 4. Okay, so hopefully you can do that. So she's going to have a spot where, since she's moving at a constant rate, you're going to have the same distance between your 3 dots. Okay. And I would like you to do this for your next class. Okay. So speed measures how fast the object's moving, but velocity tells us the direction. That's the difference. Velocity is displacement versus time. It's looking at this basically the speed in a given direction. Okay. So if we look at this chart here, so bike 1 is moving to the right, bike 2 is moving to the left. And if you look, they're covering the same amount of distance in a given amount of time. So their speeds are equal. However, the velocities, one is going to be a positive velocity, the other one is going to be a negative velocity. Bike 1 is going to have a positive velocity because that's a positive displacement. It's going from 0 to 120. Bike 2 is going to have a negative velocity according to this because it's going back to 0, which is negative. Okay. So if it's going away from the origin to the positive side, that's going to be a positive velocity. If it's going towards the origin or to the left of the origin, then it's going to have a negative velocity. But the numerical values for this particular instance would be the same. Just that one will be positive and one will be negative for their velocities. And these are looked at as your average velocity. If we look at, it covers 120 feet in 6 seconds. So that's 20 feet per second would be the average velocity of bike 1. Okay, average looks at the whole thing instantaneous. It goes to a given point. All right, so we have birds who fly in the ocean. Okay, they can fly at high speeds. The satellite data of one particular speedy albatross showed 60 miles east of the roost at 3 o'clock, and then at 15 minutes later, It was 80 miles east. What was its velocity? So here's the motion diagram for this particular bird. Okay, roost is 0. That's your origin. So it starts off 60 miles east, ends up 80 miles east. So there's our dot. And we're looking for it. There's our displacement. Okay, so we're going to take displacement divided by time to figure out our velocity. Okay, so we have our motion map set up. We know the initial and final positions, and we know the time intervals, so we can calculate the velocity. So we know it went from 60 to 80 meters, so that's 20 meters. 15 minutes is a quarter of an hour, so 0.24 hours. So our velocity then is going to be our displacement, 20 meters, divided by our time, 0.2 hours, which is 80 miles per hour. So that bird is moving at 80 miles per hour. Pretty fast moving bird. Okay, so another sample here. At t equals 12 seconds, Frank is at 25 meters. 5 seconds later, he's at 20 meters. What's his velocity? Okay, so really what we're looking at here, the 12 seconds is irrelevant. Doesn't really mean anything. So really it covers Frank in 5 seconds. Frank's going to cover 5 meters. Starts at 25 meters, goes to 20 meters. Okay, so it's going back. He's going backwards. So a negative 5 meters of displacement divided by 5 seconds of time gets you your velocity of 1 meter per second. All right, so this was a lot of information. A little bit of review here. I want you to read this little slide on vectors versus scalars. Basically, a vector quantity has a magnitude and a direction. So like 100 miles an hour north is a magnitude and a direction, so it's a vector quantity. Scalars just are numbers, like a mass, like what time it is. Okay, they don't have a direction. They are simply a scalar quantity. And we're going to draw a lot of arrow vectors during this course. Okay, that's the end of the Chapter 1 note video. Please take some time to go through and answer the questions in the formative assessment. Again, that's what we're going to cover in class. And if you have questions on any of this information, other than the technical glitch that happened when I changed slides, put them at the bottom because we will go over your responses and then your questions in class. Have a good day.